Okay, welcome here. I'm going to go over the 7.4.1 notes and homework. I'm looking at questions 4 and 5 on this video. So if you have questions on those, you can look through this video and see what we have here. So question 4, consider the experiment rolling a pair of dice. Figure 1 shows the sample space. So we've got this picture here that shows all of the sample space that we're dealing with. Each of these outcomes is equally likely. So we're going to let event A, and I'm going to try to highlight these, be the event that the sum of the spots on the sides landing face up is less than 5. Okay, so 1 plus 1 is 2. This fits in event A. There's 3, there's 4, less than 5. So that does not count. There's 3, there's 4, and there's 4. So we've got some different ones that add up to less than 5. And then we're going to let event B, and B be the event of rolling doubles. So doubles, you have 1, 2, 3, 4, 5, and 6 possibilities there. So hopefully that helps you kind of picture what I'm looking at here. Use the multiplication rule for independent events to classify events A and B as independent or dependent. So a reminder here, if the probability of A times the probability of B is equal to the probability of A intersect B, if those are equal, then these are independent events, okay? If they're not equal, then that means that they're dependent, okay? Essentially, the idea is that we don't have to worry about whether it's the probability of B given A or the probability of B to give us the independent or dependent, okay? So use that multiplication rule. So what we're going to do is we're going to look at the idea of the probability of A times the probability of B, okay? So the probability of A, okay, we saw 1, 2, 3, 4, 5, 6 yellows. Out of, if you look at this whole grouping, there's 36 different ones listed there, times the probability of B, there's 1, 2, 3, 4, 5, 6 greens out of 36 total. And if you multiply those out and simplify, you'll get 1 out of 36. Okay. If you look at the probability of A intersect B, okay, that means how many of them are in both of those things. So I highlighted yellow and green here and here. So there are 2 of them in both of those out of a total of 36. This simplifies to 1/18. Okay. Since the probability of A times the probability of B is not equal to the probability of A intersect B, then we know that these are dependent. Okay, so that's what we're going for there in that idea. This goes back way back to the one where I said, hey, you're going to find some that are dependent or independent. It's not going to make sense, but it's all based on what this is here. Is if you knew that A happened, would it affect what happened to B? If you knew that B happened, would it affect the probability of A? And the answer is yes, they're dependent on each other. Okay, letter B. Suppose that you are told that event B has occurred. Okay, how many outcomes are in B? Okay, so event B is our green. There are 6 outcomes in B. How many outcomes are in A intersect B? Okay, so we did that already. We found that there were 2. Okay, use this information to find the probability of A given B, given B using the formula. So this is saying that we know that the probability of A given B is equal to the probability of A intersect B over the probability of B. This formula you can go back in your notes and find as well, but that's what we're essentially using here. So, or it can be equal to the outcomes in A intersect B over the outcomes in B. So these were essentially 2 of the same formula, same idea. In this case, we're actually using the outcomes one. So the outcomes in A intersect B was 2, the outcomes in just B was 6, and so that simplifies to 1/3. So that's the probability of A given B, okay? Then if you answer the last question here, it says, did knowing that B had occurred, so here we knew that B had occurred, increase, decrease, or leave unchanged the likelihood that A occurs, okay? So our probability of A, if I go back to just the beginning, was 6 out of 36, which simplified to 1/6, okay? So this is my probability of A, and what I'm looking at here is this versus this probability here of A given B, okay? So we're comparing these 2 probabilities to each other, and we're talking about what we know. So did knowing that B had occurred, so that's here, increase, decrease, or leave unchanged the likelihood of it? And the answer here is increased. okay? And essentially what happened here, if you want to explain it, and I'm not going to write it down, but you can listen to it, is it narrowed the population down to only 6 sets, 2 of which were doubles, and that was a higher proportion than before, okay? So it did increase in this case. This and this are going to compare to each other. So the fact that this increased and the fact that this is dependent are going to relate to each other here, okay? If you look at number 5, so using that same set of dice, but I erased everything that I had there, okay? Number 5 says, consider the experiment of rolling a pair of dice. Figure 1 shows the sample space. Each of these outcomes is equally likely. Let A be the event that the sum of the spots on the sides lining face up is 7. Okay, so A is the event that it's exactly 7. So we want to find the sums of 7. So 6 and 1 is 7, 5 and 2 is 7, 3 and 4, 4 and 3, 5 and 2, 6 and 1. Okay, so that's my event A. And then we want event B to be the event that at least one of the dice is a 2. Okay, so we're looking at these sets here, and we've got a few more here. And some people in this one will tell me that the dice that's a 2 is 12, but you have to realize then you're counting the doubles twice. Okay, so we have to think about those different ones. So use the multiplication rule again. Okay, so we're going to look at the probability of A times the probability of B, and we're going to look at its relation to the probability of A intersect B. Okay, so probability of A was my yellow, so there were 6 out of a total of 36. Times the probability of B, we just talked about this, but there's 11 of them total there. So 11 out of 36. And that's going to come out to 11 out of 216, or if you wanted to give it as a decimal, approximately 0.05. Okay. A intersect B, so how many of them are highlighted twice? And then you've got here and here that I highlighted both of them. So there are 2 of them out of the total of 36, comes out to 1/18th, or approximately 0.06. Okay, now they're close, but they are not the same. So therefore, these are dependent as well. Okay, knowing one is going to affect the probability of the other. Okay, so suppose you are told that event B has occurred. How many outcomes are in B? Okay, list them and then count. Okay, so B, we've actually went ahead and drawn it out so you can see the color coding here. So we've got the 1 and the 2, the 2 and the 1, the 2 and the 2, so on and so forth. So they are listed. Okay, we have 11 of those. How many outcomes are in A intersect B? Those are the ones that I circled. So there's 2 of those. And use this information to find the probability of A given B. So the probability of A given B in this case is going to be the probability or the outcomes in the intersection, which in this case is 2 out of the outcomes in B, the given information, which is 11. And 2 11ths comes out to about 0.18. Okay, so letter C then again goes on to ask the question of, did knowing this information affect it? Okay, the likelihood, and the answer is yes. Okay, so did knowing that B had occurred increase, decrease, or leave unchanged likelihood that A would occur? So the probability of A we had found up here was 6 out of 36, or 1/6, okay, which comes out to about 0.167. And the probability of A given B we see right here as 0.18. Now they're close, but they are not the same. And so this answer was it increased just slightly. Okay, now that increase and dependent also go together. If it increases or decreases, they should be dependent events. If it stayed unchanged, that's when you would get independent events. Okay, so they're independent of each other. Hopefully that helped. Let me know if you have more questions.